But oh God, they uploaded my Zoom. I was unable to uh I don't know how to make it the full screen. Just a second. Oh, is it better now?
Yeah, that's fine.
Okay, fine. Okay.
Fine. Okay.
Could you go the next page?
Uh,
Yes, yes, fine, very fine. Thank you very much. No
okay.
problem.
All right.
Okay, so are you ready?
Yeah, yeah.
Okay, so let's start the morning session. So the first speaker is Professor Liang Hong from Shenzhen. He talk about higher condensation theory. So please start.
Okay. Um, all right. So, first I want to thank the organizer for inviting me to speak in this conference. So I'm gonna talk about the higher condensation theory. It is a joint work of the Zhihao Zhang and the Jiaheng Zhao and Hao Zheng. Um, well, the paper is really long. It contains a lot of material, so I won't able to cover a lot of materials, but just to give a very sketchy outline of the theory. Okay, so let me start review anion condensation theory in 2 plus 1D, okay? So the mathematical theory of anion condensation has a long history. I won't go through the history, but after many years of um, uh, the accumulated contribution from mathematicians and the physicists, and eventually the theory converts to the following format. It says that let C and D be a multi-tensor category of anions in two plus one d top-Law order. An anion condensation from C to D, which produce a gap domain wall, is determined by um, sorry, is determined by a condensable E2 algebra. The condensable E2 algebra simply means that in this context, it just means certain separable and commutative algebras. Okay, but I put the E2 intentionally because I want to say this because this is this is just a convenient way to generalize to higher codimensional defects because anion are defect topological defect are codimension too. So defect codimension two can be fused in two dimension, okay, two independent directions. So E2 algebra simply means okay, the algebra have a multiplications in two different directions, and these multiplications are compatible. So you can say that they have an algebra structure um, of a two-dimensional algebra structure in some sense. Okay, and the condensed phase D um, is again a multitensor category and is a category of is a cat. So this multitensor category is a category of deconfined particle, and mathematically it is the category of local A modules. Local A module. Now today I will also call it the E2A modules. I draw a picture here. What is the E2A module? Simply means that there is a module A X. Well, is object in D. It has A actions. The A action have the following properties. You can let A X on X along the line, or you can rotate A around X around the circle, then do the action. Okay. Um, well, then that's that's the first result about the condensed phase. The second result is that the domain wall is gapped and is contained is a cat. So M is describe the category of deconfined confined particle. What is the meaning of confined particle? So if an object in C which support a action from one direction, as I show in this picture, the Y. You see this Y? Y have a action from one side, but that does not contain a action from the other side. Okay, so in this case, A is confined. A is confined on a boundary. That's called confined particle. Okay, So M consists of confined particle and the deconfined part because the particle in D can also move on to the domain wall. As a consequence, M is the mathematically it is the category of Rayleigh modules. You can also make the bulk to wall map more precisely. This map simply tell you anyons in C and any on D, they can move on to M. You can describe this moving in a mathematical precise way. Okay, that's roughly the result. That's already this result is more than 10 years ago. Okay. Contrary to the physical intuition that a phase transition between two phases are reversible, in the sense that you all in the physical realization of phase transition, you can always tune certain parameter, and when the parameter reach certain critical value, you have phase transition. You can tune the value in the backward way. Again, you get a phase transition. So this physical phase transition is reversible in some sense. Okay. However, this mathematical description of anion condensation is not reversible because the quantum dimension of the condensed phase, the quantum dimension of condensed phase, and the quantum dimension of the initial phase have the following relations. Okay. But dimension of A, the quantum dimension of the condensable algebra is always bigger than 1 for any non-trivial condensation. Okay, so it's not reversible. So this turned out that this phenomenon is a reflection of the fact that one category of anyons, because anion is a defect of codimension 2, does not include all the topological defect in 2 plus 1D topological order because they have codimension 1 defect as well. So in this talk, I will show that by including all topological defect codimension 1 and higher, we obtain a two category and a rather complete defect condensation theory, which is ready to be generalized to higher dimensions. Okay. All right. So before we go to the higher dimension, we need to review the category of topological defect. Okay. The mathematical theory of topological defect of any dimension topological order is developed in a series of work based on the three guiding principles. One is called the remote detectable principle and boundary-Bock relation, and the third one is condensation completion principle. Preceded by some early works, this theory was essentially established by Johnson Fried in 2020 and was further developed and generalized to all quantum liquid. Okay, later. Let me summarize the main results of the theory. It says that in the n plus 1D topological order, the category of all topological defect of codimension 1 and higher form a fusion n category C, and zero morphism in C are one codimensional defect, and one morphisms in C are two codimensional defect. The K morphism are K plus one codimensional defect, and N morphism, in this case, they are N minus one codimensional defect. So N minus one is already the maximum codimension because the space-time dimension of this is already N plus one. So that means the real space-time dimension is already zero dimension. That's the minimal dimension. Okay, so the zero D defect is also called the instanton sometimes in physics. And one is a distinguished object, a label, a trivial one codimensional defect. And omega C is harm 1, 1. What is harm 1, 1? It's a category of defect of codimension 2 and higher. Because uh, because defect codimension 2 is precisely a domain wall between two trivial codimension 1 defect, right? So moreover, this omega C is a braided fusion category, N minus 1 category, is also called the E2 fusion N minus 1 category. Okay. Well, you can iterate the process by define the iterate looping. So omega K minus 1 C is the category of defect of codimension K and higher. It is turned out to be a EK fusion higher category. Okay. So I will explain the meaning of E1, E2, EK in the next slides. What's the meaning of E1 fusion? C is the E1 fusion because recall what the C is. So the C is a topological defect of codimension 1 and higher. okay? This C, okay? Require that the relation of this C and this C. We're gonna clarify the relation in later, but you can see the connection, okay? They are both C, okay? So C is a category of a codimension one defect. For a codimension one defect, they can be fused along a unique transversal direction. Okay, so that means they can be fused in one direction. Omega C is the category of codimension two defect. For codimension two defect, you have two independent transversal directions. Okay, so I draw this codimension two defect in the following picture. So A, B, C, D are codimension two defect. You can see that they can be fused in two orthogonal directions. Okay, you can fuse them horizontally. You can also fuse them vertically. So these two structure are actually equivalent. So two monoidal structure is equivalent to a braiding structure. Okay, that's why we call it E2 fusion. Similarly, if you do a iterated looping of C, it turned out to be the EK fusion. Two K codimensional defect can be fused in K orthogonal directions. Okay, so okay, that's the meaning of E1. Okay, now let me briefly mention the convention of the notation. We always use ABC with their space-time dimension to denote the topological order, and we will denote the category of all defect. That means codimension one defect or higher. Okay, by Curdy ABC. Okay, and the codimension two will be omega ABC. Okay, and codimension K will be iterated omega ABC. Okay, that's our um, notation, a conventional notation. All right. If C is nominally free, what is the meaning on C is nominally free? The meaning of C is nominally free, it simply means that this topological order can be realized by a lattice model of the same dimension. In this case, it turned out that C can be reobtained from omega C. Okay, what's the C? Is the category of a codimension one defect. Omega C is a category of codimension two defect. So this condition simply tell you that all the codimension one defect can be obtained from codimension two defect through a process called the condensation completion. More precisely, you can do it in two step. One is you do a one point delooping. What's the meaning of that? So omega one point delooping simply means that you consider a higher category with only one object, which is represented by this trivial defect, and omega C is the category one morphism of that. So B omega C really didn't do anything. It didn't add any data, any additional data. Okay, it's just this it contains same data as omega C. But next step become quite non-trivial. It's called the Karoubi completion or condensation completion, denoted as a car. Okay, together they denote called the delooping. Omega. Omega is a combination of B, one point delooping, and the car. What is the meaning of car? It says that okay, instead of just the trivial topological defect of codimension one, you need to add all codimension one defect which can be obtained from the trivial defect by condensation of any higher codimensional defect. Okay, such could be any condensation, could be other condensation, but this process will be explained in a later slide. So right now, you can just imagine that what this is a process of adding more objects other than the trivial other than the one. You need to add more. Okay. But no matter what you add, they all connect to one. Okay, because all the acts are something can be condensed from one. Okay. It will be more precise in the later slides. Physically, this condition means that physical mean, if you want to understand the physical meaning of that, it simply means that all one codimensional defect, which cannot be braided, because codimension one defect can only fuse in one direction. They cannot be braided. Braided need a two-dimensional space. They don't have a space for that, okay? So they cannot be braided. As a consequence, can only be a condensation descendant of a two codimensional defect, which can be braided and detectable by double braiding. Okay, this is some physical principle that lead to this condition of normally free condition. Let me give you one example. Okay, so in physics, there's a very famous toric code models, 2+1D topological order. It's defined if you because it's 2+1D, so the category of all defect form a fusion 2 category, but we denote it as a TC. Okay, curly TC. Okay, in this case, let's consider omega TC. Okay, omega TC consists of defect codimension 2. What's the codimension 2 in this case? Is point-like particle. It's a particle, okay? So it's anion. It's called anion. In this case, it has 4 simple objects. That means 4 simple anions, okay? They have a famous fusion rules as shown here. Okay, they're very famous. And mathematically, omega TC can be identified with the dream field center of the RepZ2. RepZ2 is the category of Z2 representations. The fusion 2 category TC consists of 6 simple objects. And well, objects are one codimensional defect, right? There are one theta x, there's few of them. So this setup is invertible domain wall realized by so-called EM duality. And the SS, and RR is a combination of 2 boundary. One is called the smooth boundary and another rough boundary. For example, SS simply mean topological defect consists of 2 boundaries, and in the middle of it is completely empty phase. Okay, but if you look from far away, this SS is really is one codimensional defect in the toric code model. Similarly, you can have RR. R is the rough boundary. Okay, because it's well known that for toric code there is 2 famous gap the boundary. One is called smooth boundary, and another is rough boundary. One is corresponding to the condensational E particle. Another is corresponding the condensational M particle. Yeah, so that's the 6 topological defect. Okay, I'll give another example. Icing. We denote the fusion 2 category topological defect in the Ising topological order by simply curly IS. Okay, in this case, omega IS. Remember, omega means codimension 2. Codimension 2 in this case again is anion. We know that in this case we have 3 famous anion. Okay, and with the well-known fusion rules. Okay, now let's ask what kind of a object in IS you have. That means how many codimension 1 topological defect you have. Well, it turned out that they only have one simple 1 codimensional defect, which is trivial one. So as a consequence, since you only have the trivial topological defect, so delooping of omega IS is nothing but just 1 point delooping. So in this case, IS is just a 1 point delooping. Okay. All right, you have more exciting examples is that it's about the trivial defect. It turned out to be highly non-trivial. We denote the category of defect of a trivial topological defect by NVAC. What is an NVAC? It consists of only trivial k-codimensional defect and their condensation descendant. Okay, for example, 0 vac is just by convention just complex number. 1 vac is nothing but categorical vector space over a complex number. So it consists of just a direct sum of finite direct sum of C's. Okay. But 2 vac is again, you do this procedure. Okay, well, it turned out that it's nothing, it's still quite trivial. It just consists of the direct sum of finite direct sum of the category of vac, the category of finite dimensional vector space. So it's still quite trivial. But if you repeat this process in the next, it becomes highly non-trivial. Uh-oh. Okay. All right. So start from n bigger than 3. You repeat this process. So n vac is the delooping of n minus 1 vac is iterated delooping of complex number. Okay. It turned out that this will not gonna be just consist of direct sum of n minus 1 vac. No, it's not. Okay. For example, in the 3 vac, it definitely contains the direct sum of 2 vac for sure. Okay. But it contains more. Okay, so when A is a multi-fusion one category, you do a delooping of that. They all highly non-trivial. Okay, and uh, they are objects in the three racks. Okay, so three rack is already highly non-trivial. Physically, what this means is the following. Remember that what are we gonna do about this delooping? We first do a one-point delooping. Okay, you start from, let's assume that n minus one vec is already well defined. You do a one-point delooping. That means you include the trivial defect. What's the trivial? What is the trivial one codimensional defect in the trivial topological order? Well, the trivial topological defect in the n plus one trivial topological order is nothing but one-dimensional lower trivial topological order. Okay, well, that's reasonable, right? Okay, so one point delooping is adding this trivial one-dimensional lower topological order. Okay, now what kind of object you need to add? Okay, that mean what do you need to add? They are called condensation descendant of the trivial topological order, n-dimensional trivial topological order. That's exactly those so-called non-chiral topological order, which have a non-trivial domain wall with trivial topological order. That means B contain a gapped boundary because this part is trivial, right? This part is trivial. So M as a gap domain wall between these two is actually a gap boundary of M. So what is called a non-chiral topological order is precisely just those topological order admit a gap boundary. Okay, then they are viewed as a condensation descendant of one. Okay, and and this M uh, which characterize the relation between one and the B is their physical meaning is precisely the physical meaning of the n minus one category M is the category of gap the boundary condition of B. Okay, so each object in M is a boundary condition of B. Well, in general, B can have a different boundary condition. Okay. All right, this will become a more mathematical. So it turned out that there is a you need a functor. You need a functor. Oh, here I should replace this bullet by one. The trivial object as one. Okay, that's also a convention. But I should change the slides. But anyway, so this is a you need a functor. Turn out that this should be fully faithful. What is the category of C? Is a C linear N category. The category of C linear N category, okay? Is fully faithful. What does this mean? This means that, well, the object of the image of this functor, well, it's some C linear category, okay? C linear N category. Let's call an object in the image of this functor a separable N category. So this give a definition of separable N category because this functor is fully faithful, so we identify n minus one vec with its image. So then the image can be, we simply say the image, the object in the image is a separable N category. So this is just simply say n plus one vec is the category of separable N categories. Okay, and you can write down this you need a functor more precisely. Once we have a definition of separable N category, then you can define EM multi-fusion N category iteratively. Okay, more precisely, let me state it. Okay, and an EM multi-fusion N category A is a condensation complete C linear EM monoidal N category such that the iterated delooping is a separable N plus one M category, N plus M category. Okay. All right, so that just means that you iterate deloop that it become an object in n plus m plus one back. Okay. If the tensor unit of the category is simple, then we call this a EM fusion category. Okay, so we have this notion. Now we have this notion of multi-fusion EM multi-fusion category. We're gonna use this notion. All right, so now we enter the main results. So condensation of topological defect. So let me state the main result. Okay, condensing a k-dimensional topological defect A in a n plus one topological order amounts to a k-step process. Okay, What do? You first a k codimensional defect A, because k dimensional by definition it is in the omega iterated omega k minus one times c, right? It's condensable if it is equipped with structure of a condensable EK algebra. That means an algebra equipped with compatible multiplication in k independent dimensions. Remember, we're talking about the k codimensional defect. K codimensional defect, it has a k transversal direction. So this algebra simply tell you, okay, this defect can be fused along k independent directions. Okay, you need this algebra in order for it to be condensable. So once you have this, what are you gonna do? You first condense A along the one transversal directions. Okay, let me, because you have a k transversal direction, right? I just denote this direction xk. And on the second one will be k minus one. You do it iteratively. The last one will be k1. So what do? You proliferate along the xk direction, okay, along the xk direction. Then you introduce interaction among the A, then it uh, produce a k minus one codimensional defect, okay? Actually, it's one-dimensional higher defect. We denote as sigma A. Okay, we denote it as a sigma A. Actually, you can compute it. Okay, you can actually compute it, but let me skip this detail. Why it is so. Okay, but that's the main result. I will just give you some illustrating example later. So it turned out that this omega A is naturally equipped with a structure of condensable EK minus one algebra. Okay, why is the EK minus one? Because when you do a proliferating A along the one XK direction, and when you introduce the interaction among A, you basically define the interaction using the algebra structure along the XK. Okay, along the direction of xk. Remember, A have a algebra structure, multiplication in all k dimension. You only use the multiplication in one direction. Okay, as a consequence, because you only use the multiplication of A in one direction, there is still k minus one multiplication left. As a consequence, sigma A has a k minus one multiplication. So it's the condensable EK algebra. Then you can repeat the process. Okay, so now you can further condense along one of the remaining transversal direction, let's say xk minus one, and using proliferating in this direction, then introducing interaction, then you got sigma 2a, which is k minus 2 codimensional defect, so on and so forth. Okay, you repeat the process. In the last step, in the case step, you're condensing a one codimensional defect, omega k minus 1a, along the only transversal direction, which defines the phase transition to a new topological order. Well, this topological order is called the Morelli equivalent to C, which is shown in this picture. So C and D share the same bulk. So they are the boundary phase of the same one-dimensional higher topological order, and they're connected by a gap domain wall M. Okay, in this case, the condensed phase can be computed precisely. So the category, so remember our notation convention. So the condensed phase is denoted as dm plus one, and the category of all defect of D is denoted by curly D. Okay, so this curly D, it turned out to be can be computed as the E1 module over sigma k minus 1a. What is the meaning of E1 module? Well, that's just a bimodule. Okay, that's a familiar notion, just a bimodule of this algebra in C. That's a deconfined particle. Deconfined defect. Why is it deconfined? Because you have A action, one-dimensional A action. One-dimensional A action have two, you can have two action, left action and right action. Okay, that's deconfined particle. This particle can be moved along one direction. So that's deconfined. But if you only have one side, well, then you cannot move. Okay, so if you only have one side action, that's right A modules, modules, that become confined. So that would define the domain wall. So you have a formula, precise formula to describe the category of boundary condition on the domain wall. Okay, in this formula. All right, you can have more fancy formula, which I'm not going to explain to you, but I'm just tell you this theory can make the calculation more efficient. For example, you want to compute what is the k codimensional deconfined particle or deconfined topological defect. That's just omega iterated omega of d, right? But it turned out it can be computed by some kind of a higher EK modules. So this is just given by some higher repetition theory. I'll skip some detail because I won't cover this. All right, the last thing I want to mention of this main result is that when C is anomaly free, when C is anomaly free, as we mentioned before, C is, can be recovered from omega C by delooping. Then the same phase transition as a k-step process can be alternatively defined by replacing the last two steps by a single step by condensing sigma k minus 2a. What is sigma minus 2a? This is a codimension 2 defect. Okay, so this simply says that if C is anomaly free, you don't need to condense along another line then got the codimension 1. You can just do the combine the last two steps into one. So what that means? That means that you can proliferate this co-dimension to defect in a region, then introduce the interaction, then you got a condensed phase, as shown in this picture. Okay, this is proliferating, and this is the condensed phase. Okay, then in this case, you can also compute the D precisely. Remember, omega D is the co-dimension 2 defect. Okay, it can be computed directly using E2 module. That's again, this is a local module. Okay, and you can also compute the D as recover the D as the delooping of omega D, and similarly, you can compute the M. Okay, first compute the omega M. Okay, then do a delooping. It turned out that if n equal 2, this modified last step is precisely your anneal condensation theory. Okay. And the condensable EK algebra A is called Lagrangian if the condensed phase is trivial. Okay, that's the same as the anneal condensation story. If the condensed phase is trivial, what we call the algebra, condensed algebra, Lagrangian. So let me give you some simple example. For a topological order, we know that you can it's well known that there is a Lagrangian E2 algebra. You can condense it directly. That's your anneal condensation theory. But in the new theory, you can do it instead of condensing the anion in the two-dimensional space directly. Well, you can first condense it along the line, then produce a one-dimensional higher defect. We denote as omega AE. Well, in this case, this is precisely just R. What is R? R is the codimension 1 defect made out of the two rough boundary. You're just putting two rough boundary together, they become a codimension 1 defect. Okay, then you condense this rough boundary. What do you got? You got a trivial phase. Okay, it's very easy to imagine by proliferating this RR. And R in the middle of the R is empty phase. By proliferating this empty phase with rough boundary, you simply making the topological order more and more trivial, more and more empty, right? More and more places have empty. That by introducing interaction, you remove the boundary, then everything become empty phase, just trivial phase. Similarly, you can also do the other Lagrangian algebra. Okay, let me skip the detail, but in this case, you simply get a smooth boundary. Okay. The answer is it's the condensed phase is the same. Okay, but let me give you a for the I think I probably don't have enough time for that. So let me skip some detail. Okay, this become very so. Let me just give you one interesting example and making this a lot of fun, I guess. So let's consider the case that we start with the quite trivial case. So the initial phase and the final phase are both trivial. Okay, consider this case. They're both trivial. And then you have a gap domain wall, right? Because this C and D are both trivial. What's the gap domain wall? The gap domain wall is nothing but the 2 plus 1D anomaly-free topological order. So, okay, so this domain wall is precisely anomaly-free topological order of 3D, okay? But we know that these topological order can be described by a pair, just like the theory of anneal condensation. C is a chiral central charge, and B is a multi-tensor category. Okay, All right, just remember the meaning of B. That's enough. Okay, now we do a very interesting process. Now we roll up this top load order. By rolling it up, what do we got? We got a cylinder. But by shrinking the cylinder, what do you got? By shrinking the cylinder, you simply got a string in three-dimensional space. Okay, so this is 3 plus 1D. So the spatial dimension is 3. So this is a membrane in the 3 dimension. Okay, by rolling it up, we got a cylinder. That's a string. Okay, what is this string? A string is a codimension 2 defect, right? It's codimension 2. So it must be an object in the category of two-dimension 2 defect in trivial topological order, 3 plus 1D. But remember that the topological defect of the trivial topological order, in this case, is 3-vac. If you by looping, you simply got 2-vac. 2-vac is the category of codimension 2 defect. Okay, but we said that this string must be a one of them. Which one? It turned out that it is precisely B. B is a module tensor one category, should be viewed as an object in 2-vac. Okay, it turned out that this B is nothing but condensable E2 algebra. Okay, so as I showed in here, so this is precisely the object D. By condensing it, what happens if we condense the string? We obtain omega D given by the E2 module by our formula, right? We have this formula, so so just plug into the formula. You know how to describe the condensed phase, right? Actually, in this case, I usually use this formula. Use this formula because it's codimension 2. Okay, so omega D can be computed directly. Okay, omega D can be computed directly, and it turned out it should be trivial. Wow, that's interesting. After some process, you compute it become trivial. That means, oh, okay. So if you by rolling it, by rolling up topological order, you got some non-trivial string, but you condense it in the trivial phase. You again got a trivial phase, but this condensation is not trivial. Yes, the condensed phase is trivial, but what is the gap domain model you got? It turned out that the gap domain model you got is exactly M, nothing else. Okay, that make it very interesting because the condensed phase is trivial. So this B is a Lagrangian algebra. All right, so module tensor category is a Lagrangian E2 algebra in 2-vac. Okay. All right, so let me give you one non-trivial example. If C is anomaly free, I just talked previous example, the condensed phase, the starting phase is trivial. Let's consider an anomaly free one. If it is anomaly free, in this case, C is equal to the delooping of omega C. It's by a theorem by Galto and Johnson Fried. I should add a reference here. This omega sigma omega C can be computed by the right module over omega C in a vac. Okay. These actually provide a concrete coordinate system to a non-degenerate diffusion N category. Let me make a comment is that like similar to differential geometry, if you want to compute something, you always choose a coordinate system. You compute it in a chart. Okay, if you want to compare different computation, you need to know the translation function between different charts. So here is similar. If you want to do a computation in an abstract category, you better provide a coordinate system. So this can be viewed as a coordinate system. Once we provide a coordinate system for C, you can describe condensations precisely. Okay. And it's okay. Indecomposable condensable E1 algebra in C are precisely indecomposable multi-diffusion N-1 category A equipped with the central functor. Okay, central functor simply means there is a braided monoidal functor from omega C to the dream field center of A. Okay, if this braided functor is a braided equivalence, then the condensable E1 algebra is Lagrangian. Okay, in the sense that the condensed phase is trivial. Okay, so in this case, of course, you can apply the formula. You have a formula for D and the precise formula for M as given in the abstract theorem. But this might not make any sense to you, right? So you want to ask, what does this abstract data, which define the abstract algebra, has any direct physical meaning? Yes, indeed. So this physical meaning come from this formula. If we compute M precisely, you will see what's going on. So let's compute it precisely. So M is this formula. You compute it precisely. What do you mean compute it? You simply only thing you need to do is compute the omega M. Omega M is distinguished object M label. So so M is a distinguished object in M. The label a particular boundary condition or domain wall condition. So this in M, small m, label a particular domain wall. Then omega m is the topological defect living on this particular precise particular gap the boundary. So omega m is the topological higher codimensional topological defect living on this boundary condition is a fusion category. If you compute it carefully, it's A. Okay. What does it mean? Remember that we start with the A. A is the condensable algebra. So it means if you have a C and a D have a gap domain wall, then this gap domain wall, sorry, the topological defect, the fusion higher category of topological defect living on this gap domain wall with the fixed gap wall condition is precisely a codimension one defect. Well, we not only, but
Sorry,
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 it's precisely a
40 minutes
condensable
now,
E1
now
algebra.
has passed. So could you summarize?
Oh, okay. Let me summarize. So this is one of the. All right. So maybe the only thing I want to show just in the end is that you can really make the calculation more precise by computing the G gauge theory, because I don't have time for that. But this slide will show you that you can make the calculation more precise by choosing a proper condensable higher algebra by do a delooping repeatedly, and eventually you can compute the condensed phase, which is given by you start from a G gauge theory, you can get a H gauge theory. So this example to show you that this theory is computable and work for all dimension. All right, thank you very much.
Okay, thank you very much. Okay, so is there any questions or comments? Yeah, please.
Thank you for the talk. Can I ask a few
Thank you.
questions? Oh, actually two.
Yeah.
Uh,
Okay,
so,
sure.
uh, so in 2D case, what people call Lagrangian subgroup is equivalent to Lagrangian E1 algebra in your notation?
E2 algebra.
E2 algebra.
So, yeah.
I see.
Let me make the more. So when people talk about the Lagrangian subalgebra, that only work for finite abelian group case.
Aha,
So let me make it more precise. When the C is the dream field center of the rep G, and when the G is only a finite abelian group, that's a very special case. It's not general. In that case, a Lagrangian algebra is same as a Lagrangian subgroup.
I see. Can you identify like E2 algebra by mutual statistics between part topological defects? Like in the Lagrangian subalgebra case, the anyons in that subgroup must be mutually, identity breeding statistics. Can we
Right.
identify
Yeah.
is similar method?
Yeah. I shouldn't say and then a same method. There is a generalization of that. Okay, so because as I said, Lagrangian subgroup in that case, everything is mutual, right? And in that story, it's a little special case. Sometimes does not allow you to see a precise formulation because it's too special. Very often you don't see the algebra structure. So what happened is in general is that you will also get something similar, which says that the twist of A. A in this case is a composite particle. Okay, it is a direct sum of simple object. But now we require the condensable E2 algebra have a defining property which says that the topological twist of A is trivial.
Mm-hmm.
That's somewhat similar to what do you have for self statistics is trivial in some sense, or the particle have a mutual trivial gradings. But in general, you have to relax that condition by saying you have some kind of local property, symmetric property respect to the multiplication of A. That's the that defining property of E2 algebra.
Thank you.
Yeah.
And the
Yeah.
second question is, can we have some kind of indicator that showing two categories in the connected by some condensation? Like do they have a same total quantum dimension or?
Uh, well, if you talk about only if you restrict your discussion to 2 plus 1D, yes.
Yeah.
In
That's
this
what
case,
I'm interested.
okay. If you only refer to this case, I will say yes. There is a way to characterize that, but not by quantum dimension. Instead, it's called weak equivalence. So that means two topological order are connected by a gap domain wall. Then they were called weak equivalence. And in this case, so that means any topological order, if they can be connected by that gap domain wall, their condensation, that you can using certain condensation to obtain one from the other, but not necessarily from any condensation. Any condensation, no. Okay,
Okay,
but you
thank
have
you.
to generalize. You have to generalize any condensation to condensation of codimension 1 defect.
I see.
Yeah,
Thank you.
you're welcome.
Okay, so any other questions? Okay, so if not, so let's thank the speaker again. Thank you very much.
Thank you. Thank you.
と、次はどうしましょう。いや、
すぐに用意してもらって。
まあ、はい。Okay, so next talk will start soon. Okay.
あ、ここでもいい。あ、あ、はい。
Are you ready? It's okay.
OK。
Okay, so the second speaker is Kohei Yamaguchi-san from Nagoya. Please talk about equivalence K homology of affine glass manion. So please start.
Thank you for introduction. I'm Yamaguchi from Nagoya University. Today I will be talk topic with the following title. This talk is based on joint work with Takeshi Ikeda from Waseda University and Maximo Zono from Virginia Tech.
So please make screen sharing. Screen share.
あ、スクリーン
This
シェアで
is
きてない。
on hybrid workshop. So please make screen sharing. Otherwise we cannot see.
あなたのズームアカウント。あ、これできてないですか？あれこれ、あれれこれ、もう一回ちょっとじゃあ、で、さっき今、だような。あ、もしかしてネットが弱いからラグでもしかしてっていう。あ、じゃあちょっとネットを変えます。じゃあ。で、これで、OK？ これ、いけてます。OK。
Sorry, can you see his slide from online?
Not yet. Not yet.
It's okay?
No. I cannot say anything.
向こうは、向こうで見えてない。
From here, there's a slide with participant's name. So, yeah, a little bit small, but it would be okay. Could we continue?
No.
No? How about from other people? No reaction.
Yeah, I think I can see the slides from here.
Yeah, I can see. I can also see the slides.
You can see the slide and you can understand what written.
Yeah,
But
I can see it.
Hayashi-san has a problem.
I cannot see it.
どうしましょ
一応どうしたらいいかな。ネットはもう大丈夫そう。ネットは大丈夫。
This one? Maybe other person make a screen sharing, but only me cannot see.
う。Hayashi-san, you can see nothing.
No. Wait. I will check the. これか。
Is this perhaps your local problem? Here, the screen in Nagoya, it's okay.
I know. そう20だから。Okay. So, YouTube sharing is okay. So then, okay, you can start. Okay, no problem. So, only
Okay. So,
problem. So, that kind of, なんだ。
okay.
YouTube is okay. So, no, okay, you can go.
OK?
Okay.
It's OK.
Okay.
Sorry. In this talk, I plan to explain the following topics in order. Please note that this slide is available on the website this workshop. This talk is related to one of the fundamental problems in Schubert calculus. I will start by inducting a classical problem in Schubert calculus. This classical problem, when four lines are given in three-dimensional space, how many lines can intersect with them? Schubert used principle of conservation of the number to compute various enumerate problems of this type, which led to the naming of the field as Schubert calculus. In modern mathematics, it can be interpreted and determine the product structure constant related to the Schubert class in cohomology and case theory of Grassmannian. Grassmannian refer to the projective variety from the two-dimensional linear subspace in C4. Next, as a prototype, I will introduce the following theorem. Next, as a prototype, I will introduce the following theorem, the set basis of the cohomology of Grassmannian, indexed by partition of length d or less. With first component, lambda 1, is length is n minus d or less. The sigma lambda is defined the Schubert varieties with cross the variety of Grassmannian, and these are named as Schubert class. This result claims the cohomology of Grassmannian can be realized as a quotient of the ring, symmetric function in the variable. Interestingly, sure polynomial which correspond to the character of irreducible representation of GL. Provide this isomorphism. So, in particular, note that this isomorphism claims the productive structure constant of Schur polynomials and Schubert classes coincide. Here, few examples of Schur polynomial. Okay. Next, Grassmannian has representation as homogeneous space like this. PD consists of all block matrix with 0 in the lower left, and this named as a parabolic subgroup. The affine Grassmannian, which is mentioned in the today title, is version of the loop space of Grassmannians. This is referred to as a set of C-valued points. So our interest is the equivariant K-homology of affine Grassmannian. Here T is maximal torus of GL, which consists of all diagonal matrix, and RT is its representation ring. So the Schubert class is equivariant K-homology of the affine Grassmannian are indexed by the what are called zero Grassmannian element. Sorry. I will explain this in more detail later. Let me briefly explain why we focus in equivariant K-homology of affine Grassmannian. The existence of the what is known as a K-theoretic Peterson isomorphism is very important. The equivalent quantum K-theory of Flack variety is currently the most generalized algebra available for developing Schubert calculus. The product structure constant of Schubert class in quantum K-theory are known as K-theoretic Gromov-Witten invariant, which are of great interest. We aim to compute these effectively from the affine side. So, here is the main theorem we are introducing today. We introduce good function that represents Schubert class in equivariant K-homology of affine Grassmannian. And we obtain isomorphism as a RT algebra generated by this function. This can be seen as variant or generalized of the relationship between the cohomology of the Grassmannian and Schur polynomial mentioned earlier. あ、the function GW that represents the Schubert class is called theoretic WKK sure function. I will introduce its definition and properties. To do this, let's first review the root system of GLN. Let X be the character group of T with a basis denoted by AI. Let Q the root lattice and phi the root system. We denote their dual as X check, Q check, and phi check. The linking diagram looks like this. So we denote the while group of GL as WZ. So the generators are S1 S minus 1. And this is isomorphic to the symmetric group of degree n. The group obtained by the semi-direct product with the translation of the colute lattice is called the affine while group. The generators are S1 S minus 1 along with an additional S0. Furthermore, the while group obtained by extending the colute lattice to X check is called the extended affine while group. This can also be written in this way. X check over Q check is isomorphic to fundamental group of GL. And we denote its generator as tau. The extended linking diagram of GL is like this. The role of tau can be interpreted as the rotation of linking diagram. Next, we collect the element of the extended affine while group that when multiplicative on the right by the generator, multiplicative on the right by the generator of the while group increases in length. This set is denoted WG0, and it's called the zero Grassmannian element. The zero Grassmannian elements correspond to 1, the partition where the first component is less than or equal to n minus 1. Let me explain this with an example setting n is 4. We prepare a table with periodical 0, 0, 0, 0, 1, 1, 1, 2, 2, 2. So here we consider the 3 bounded partitions 3, 2, 1. In this case, we read the table from bottom to top and right to left, defining W lambda as follows. S2, 0, 0, 3, 0, 3, 2, 1, 0, 2, 1, 0. I have also included other example is here. Sorry, next, we construct the action of the level 0 affine K-Nilfecke algebra on the ring of symmetric function. Here we define the equivariant parameter Bi. Sorry. We will prepare main tool for defining WK-K-Shio function. First, we define the action of the extended affine while group on RT in this way. So note that the translation acts trivial. So we consider the localized ring RT delta. We define the group ring KG delta, twisted by the smash product. We consider the element Ti and Di, which are called de Major operator. These satisfy the braid relation. Yeah. These satisfy the braid relation of type N1. From this fact, TW and DW are determined by general element W of the extended affine while group independently of its reduced expression. The subring span by TW is denoted by KG. This is called the level 0 affine K-Nil-Heck algebra. Next, we construct the action of the level 0 affine K-Nil-Heck algebra on the ring of symmetric function. Here we define the equivariant parameter Bi in this way. Lambda is the ring symmetric function on invariable y1, 2, 10, dot, dot. Lambda hat is its completion ring. We denote the coefficient extension of this R to RT as lambda hat RT. Now we construct the action of KZ on lambda hat RT as follows. The while group act only the equivariant parameter as permutation of index. The translation part act multiplication by as an infinite product at omega. So under this action, we define the W1 as GW, which we call the WK-K-Shio function. As mentioned initially, the function represents the Schubert class in equivariant K-homology of affine Grassmannian. So here I will provide simple examples. So non-trivial. Non-trivial note that it can be expressed in terms of shear function of hook type. This. Okay. Okay. So finally, I would like to introduce result reading the WKK shear function of rectangle type. Here we consider those include rectangle within the K-bounded partition where the sum of the length of the side equal to n. In this case, the WKK shear function for rectangle type can be factors. This fact is based on the understanding that the WKK shear function of the rectangle type is, in fact, the tau function of the relativistic Toda equation. Within that, I conclude my talk. Thank you for your attention. Thank you.
Okay, thank you very much. Okay, so is there any question or comment? Feel free.
So you mentioned as a motivation, K-theoretic Gromov invariant. Are there any other motivation for your work?
I have mentioned represent theory and this sorry. I want to understanding semi-infinite Flach manifold KQZ national C valued point. CV relation over N E torus H T.
Can you answer in brief? I only ask, there are other motivation for it or not?
Yes.
Not in detail.
Yes. So I want to
maybe some of keywords.
Yes. K-nil Daha, double affine Hecke algebras action on semi-infinite K cohomology, equivalent K cohomology. ちょっと以降のK-nil Daha. So it's this geometry. I want to geometry of semi-infinite Flach manifolds from K-nil double affine Hecke algebra.
Oh, I see. And second question is slightly technical. In the final part, you mentioned relativistic Toda equation.
Yes.
Is it related to eventual theory of J function or something?
Yes. This.
So it's some K-theoretic extension of eventual theory.
Yes.
Okay. Thank you very much.
So is there any other question or comment? Welcome from online. No? Okay, so if not, so let's thank the speaker again. Thank you very much.
Thank you.
Okay, so next talk is as scheduled. Okay. Within 1 minute.
あれこれで。
Professor Kim Lee-san, are you here?
Yes. Can you hear me?
Yeah.
Okay, so let me share my
Yeah.
slide.
Yeah, fine.
Okay.
Could you go to the next slide?
Sorry?
Sometimes this slide becomes freeze. So I would like to check. Well, before that, yeah, you can make a full. Yeah. And yes, that's fine. Okay, so let's start. Okay, so next speaker is Professor Kim Lee from Shenzhen. He'll talk about quantum Twyman lemma in geometric quantization. So please start.
Okay. Thank you very much for the introduction. And I also want to thank the organizers for the invitation to give a talk here. The title is Quantum Twyman lemma in geometric quantization. And in this talk, I will introduce some of the joint works with Kowei Chen and Conan Liang from Chinese University of Hong Kong on quantum Twyman lemma in geometric quantization and its applications. So my talk will consist of 4 parts. I will start with some background in geometric quantization and Berzin Toeplitz operators. And then I will give a revisit of Tuiman's lemma in geometric quantization. And I will introduce also the motivation for our work on the so-called what we call our quantum Tuiman lemma. And the method is based on the quantization, Kähler quantization via Kapranov's L infinity structure. That's our main technical tool. And then finally, I will introduce our main results, the quantum Tuiman lemma and its applications. Yeah, so let me start with some background. So the mathematical theory of quantization, so the phase space of a classical mechanical system is described geometrically as a symplectic manifold. The mathematical formulation of quantum mechanics is in terms of operators on Hilbert spaces satisfying the so-called Dirac axioms. So there are two schemes for quantization on symplectic manifolds. One is the deformation quantization, which focuses on the algebra or the quantum algebra of operators. And the other is geometric quantization, which focuses on the Hilbert space of the quantum system. So the construction of geometric quantization, or equivalently the Hilbert spaces, actually depends on a choice of polarization. There are two types of polarizations. One is a real polarization, and the other is complex polarization. So we will, in this talk, we will focus on complex polarizations on symplectic manifolds, which is equivalent to a complex structure compatible with the symplectic structure on the phase space, making it a Kähler manifold. Yeah. Okay, so on a Kähler manifold X, the Hilbert space of level K of the geometric quantization is defined as the following space. The curly K is the space of holomorphic sections of the K's tensor power of the pre-quantum line bundle L. So here we actually require that the Kähler manifold is so-called pre-quantizable, meaning that there are certain integrality conditions, so we can define the pre-quantum line bundle L. So this is the Hilbert space. And on these Hilbert spaces, we can define the so-called Berzin Toeplitz operators associated to any smooth function f on X. So it's defined as the following composition. So you take a holomorphic section, and a simple thing is you can multiply it by the smooth function. But the output is not holomorphic anymore in general. And so what we need to do next is we need to take the orthogonal projection, capital pi k here, from the big space of smooth sections to the Hilbert space, which is a smaller space of holomorphic sections. So this is the definition of Berzin Toeplitz operators. And the interesting thing is, if you take two functions, two smooth functions, f and g, you take the composition tfk with tgk. It has the following asymptotic property as k goes to infinity. So in other words, you take the composition, although in general it's not a Toeplitz operator on the nose, but we have the following asymptotic formula. So the first term on the right-hand side of this asymptotic formula is the classical part. So that's Toeplitz operator associated to f times g. And then we have some higher order terms. So we also have some functions related to f and g. So this is ci f g, and it satisfies the locality condition, meaning that ci f g is a bidifferential operator acting on this f and g. So in particular, if you take C1, Fg minus C1 GF, namely the commutator. And then you actually get a constant multiple of the Poisson bracket. That's where you can see the simplex structure there. And this actually gives rise to a deformation quantization of smooth functions on X. So if you turn this 1 over K into the formal variable H bar, because you have this asymptotic thing, so you can turn this 1 over K to this formal thing. And this is how we, this is a so-called Berzin Toeplitz deformation quantization. And this is the quantum algebra of operators on the Hilbert spaces. So in general, deformation quantization is an associative but non-commutative deformation of the algebra of smooth functions on symplectic manifolds. So this is a definition. So actually, if we want to define only deformation quantization, so you actually don't need the polarization data, because polarization data is actually essential in the definition in the definition of Hilbert spaces, but not on algebra, quantum algebra. So here, a deformation quantization is an associative product on C infinity on smooth functions on M with a formal variable H bar, such that we have a formula. So you can see that this is actually so actually this is consistent with the Berzin Toeplitz, the asymptotic formula for Berzin Toeplitz operators. And here CIs are bidifferential operators with C1 Fg minus C1 GF equals the Poisson bracket. Okay, so now, so any questions? Okay, so this is like the background. So now let me move to the so-called Twyman's lemma in geometric quantization. So this is a so let me first state this this lemma here. So for every smooth function and any two holomorphic sections, so here we can see vectors in the Hilbert spaces and also elements in the quantum algebra. So there is a following equality. So we take the canonical connection on the pre-quantum line bundle and also its tensor powers. And for every smooth function, we have an associated vector field because we have this simplex structure and we denote it by XF. So this connection acts on the first holomorphic section S1 plus 1 over K times delta F. So here delta is the Laplacian on X because we have this Kähler structure. We also have metric, so we can define the Laplacian here. And times S1. And what we now call this an orthogonality relation. So we have an operator XF, nabla XF, plus 1 over K times delta F multiplied by this function. So this is, since this holomorphic section S2 is arbitrary, both S1 and S2 are actually arbitrary. This implies that this operator, which is actually a differential operator, first order differential operator, because here we have this connection, and here we have this function delta F multiplied by S. So this is a first order differential operator. It actually lies in the orthogonal complement of the Hilbert space inside the bigger space of all smooth sections. So this is kind of interesting because you start with S1, which actually lives in H0, and then it ends up, the output actually lives in its orthogonal complement. So this is a very simple interpretation in terms of the linear algebra. Okay, so we have this differential operator, and it's from H0 to actually the output is a smooth section, but actually I can make this more specific. Actually, the output actually is H0XL tensor K perp, means it's orthogonal complement. So this is actually a starting point for this series of works. And so our question is very simple. So is this a simple coincidence? I mean, you get an F, then you can define an associated differential operator so that it has this interesting property. So why is this property interesting is because so you recall that when we define the Brazilian-Toeplitz operator, so you have to take certain orthogonal projection to the space of holomorphic sections. So from a mini algebra point of view, so its orthogonal complement is also interesting because of this decomposition. That's you know both parts and you know this decomposition. So is this like a coincidence, or are there other differential operators associated to smooth functions such that they share the same property as in Twyman's lemma? Meaning that so the domain of this map is actually a holomorphic section, but the image is actually its orthogonal complements. And also this kind of nice results should have interesting applications. And so that's, and actually I will, later I will also say some motivation why, some hints why we actually consider this, these questions. Okay, and so now let me explain the main technical tools for solving this question. This is the so-called quantization, or more explicitly, Fedosov quantization of the L-infinity structure on Kähler manifolds. So that goes back to 1996. Kapranov discovered an L-infinity structure on Kähler manifolds. So in his study of Rosansky-Witten theory. So the main ingredient of this structure is actually a cochain complex whose cohomology is isomorphic to holomorphic functions on the Kähler manifold, which gives an equivalent description of the complex structure, or equivalently the complex polarization on the Kähler manifold X. And the theorem, so in our joint work with Chen and Cornelian, we proved that there exists a Fedosov connection D on X, which is a quantum extension of Kapranov's L-infinity structure on Kähler manifolds. So the reason we call this a quantum extension is as follows. So if you only consider holomorphic functions, then you don't, then you get nothing different. So that's like that's what we use the slogan that there is no quantum corrections to holomorphic functions. But if you consider instead of holomorphic functions, but also all smooth functions, then you will get a certain quantum correction. And if we go back to the definition of Brazilian-Toeplitz quantization, this is not that surprising. So let me go back to this definition here, because the Toeplitz operator is defined as the multiplication by a smooth function, and then we do this orthogonal projection. But you think about this. So if usually we consider compact Kähler manifolds. Now let's consider general non-compact thing, and you can multiply it by a holomorphic function. Then you don't need to do this orthogonal projection at all, because the output is already holomorphic. So that's that coincides with the fact that in our Fedosov quantization, when you start with a holomorphic function, you don't get any quantum correction. That's consistent with the classical data. Yeah. So so according to these first results, this Fedosov connection actually induces a BB quantization of the Kähler manifold X, but I don't have time to explain what is a BB quantization. And the interesting thing is that in Fedosov's original construction, he only uses the symplectic structure. So what he did is on a general symplectic manifolds. But in our work, this quantization actually encodes not only the symplectic structure, but also the complex geometry of this Kähler manifold. And as I said before, the Hilbert space actually, to define the Hilbert space, actually you need this polarization data. Now, in this Fedosov connection, we have this polarization data. So is it possible to like extend Fedosov's work not only on quantum algebra of observables, but also on Hilbert spaces? And yeah, so I will say that later, and so but let me briefly describe this Fedosov connection, or equivalent is a quantum master equation in BB quantization. So the idea behind Fedosov's original approach to deformation quantization is as follows. So on a Kähler manifold, or more generally on a symplectic manifold, you can define the Weil bundle over the phase space. And then there exists a fiberwise star product, which describes the local picture of quantization on the flat space. And the Fedosov connection actually gives the gluing data for these local quantizations, which is of the following form. So it's nabla is the Levi-Civita connection on Kähler manifolds. So there's a canonical one. Plus 1 over h bar, this gamma bracket with something. Here the bracket, this is the bracket associated to the weak product, or the fiberwise star product. And this gamma is actually one form valued in the Weil bundle. And the flat, the main the first main result is that the first main result in Fedosov's construction is that the flat sections under these connections are actually isomorphic to the quantum observables. That's a smooth function with a formal variable h bar. Okay. Yeah, so this is the original construction, and its goal is to construct a deformation quantization or equivalent is the quantum algebra of observables. And we actually follow the same line of thought and give a construction of the so-called Bugman-Fogg bundle on Kähler manifolds, which actually gives rise to the Hilbert spaces in geometric quantization. So we start with the fiberwise Bugman-Fogg action of the Weil bundle. So this is a complexified Weil bundle, and we also have a holomorphic Weil bundle, which roughly speaking is like half of WXC, meaning that it's the completed symmetric product of the holomorphic cotangent bundle. But in this complexified Weil bundle, we have not only holomorphic cotangent bundle, but also anti-holomorphic cotangent bundle. And we denote this action by this symbol here. And now, if we twist this WX, this is the holomorphic Weil bundle with the tensor power of the pre-quantum line bundle L to the 1 over h bar, we obtain the Bugman-Fogg bundle, we denoted by curly F sub x, as a module sheaf over the Weil bundle with respect to this fiberwise star product. Then there exists a Fedosov connection on this Bugman-Fogg bundle of the following form. So you can see that this looks very similar to the original Fedosov connection. The only difference is that, so there are two main differences. So in Fedosov's original work, this is the bracket associated to the Weil to the star product. Now here, this is the Bugman fork action. And also here, the connection is a little bit different because you need not only the Levi-Civita connection, nabla X, but also the connection on this pre-quantum line bundle. But other than that, you can see that it's quite similar. Now, the theorem is that so it's not only it doesn't only look similar to the original Fedosov connection, but it's actually compatible with the original one. Okay. Okay. So because we have this, so alpha here is a section of the while bundle, and S is a section of the Bugman fork bundle. So we have this action here as a module here. And so this connection satisfies the Leibniz rule, meaning that it's compatible with this module action. And if you take another thing is if we take the evaluation, let the formal variable h bar to be 1 over k, then the flat sections of the fork bundle is actually isomorphic to our Hilbert spaces. Now, this is what we call a co-chain complex model of the Hilbert space. So we should say that it's another co-chain complex model because originally this is the H0, the holomorphic section. So you also have this D bar. You also have that complex. And you take H0, you get the Hilbert space. So here, by using this Fedosov construction, we find another co-chain complex model of these Hilbert spaces. So these results actually imply that we obtain a quantization scheme which involves both quantum observables and the Hilbert spaces as the modules over quantum observables using the language of formal geometry and homological algebra. I mean, what we call the Fedosov construction. Here, let me say a little bit because I didn't get into too much details. So there's a little bit trick about this h bar here because h bar is originally defined as a formal variable, but then you take the evaluation here. So we should be a little bit careful here. So, when is this well defined? But this is like the detail, so I'm not going too much into it. Okay. So now we on this while bundle we actually have an interesting weight. So that's how we can actually apply this this Fedosov complex, what we call the Fedosov complex, to a quantization of the Riemann lemma. So we actually focus on the Brazing-Toeplitz deformation quantization and denote the corresponding Fedosov connection by D sub BT. So BT here is short for Brazing-Toeplitz. So this actually induces a co-chain complex because the flatness of this DBT implies that we actually get a co-chain complex. We call this the Fedosov complex. Now we define a weight on the formal while bundle by assigning weights on generators. So we assign weight 1 to h bar. And we assign weight 1 to those anti-holomorphic terms, to those anti-holomorphic, those sections of the anti-holomorphic cotangent bundle by 1. But for those holomorphic cotangent vectors, we assign weight to be 0. And it's not difficult to check that the fiberwise weak product on this while bundle is actually compatible with this weight. Meaning that you take two monomials and you have certain weight and you take the star product and then the output, the output have the same weight. This is the meaning of this compatibility. Okay. So let me give you a more direct way to see these weights here. So we draw this picture here. The horizontal direction denotes the power of H bar, and the vertical direction denotes the polynomial degree in the anti-holomorphic wire bundle WX bar. So the weight is then simply the sum of the x coordinate and the y coordinate. And so here, each line here denotes the terms of the same weight. For instance, the first one here, this is the weight 0. And then we have this first line here, those terms along this first line, is of weight 1, and then weight 2, and weight 3. So it's like this. Now, yeah, so now we want to define certain differential operators. So this is how we can see the differential operator in Tolman's lemma, and also how this can be generalized to obtain a quantization. Okay, so this is the main result in the serial Fedosov quantization, is that given any smooth function f, so there is a uniquely determined flat section of the Weil bundle, so that its symbol is simply f. So by symbol, we simply mean because we have polynomial degrees in the cotangent bundles, so we simply take those polynomial terms, we assign 0 to the polynomial terms. In other words, the symbol simply takes the fiberwise constant term, and you simply get a function. And this is also generalized to the Bachmann-Fock module case. We also have a one-to-one correspondence via the symbol map, and this is explicitly how we get the Hilbert spaces. Yeah, so this is now the interesting thing. Now using the weight I have just defined on the Weil bundle, we can decompose a flat section OF as follows. So we have OF, and we have the weight 0 components, we have the weight 1 components, and all the high order terms. So in general, for a smooth function, this will go infinitely. So we have in other words, we have a formal power series in both H bar and powers of the anti-holomorphic cotangent bundle. So now we are ready to define a series of differential operators while the Fedosov quantization. I will explain later why these are differential operators. So for each weight m, which is positive or 0, we let gamma fm. This is gamma fm is the differential operator. So we define it as follows. So we use So for this holomorphic section of the pre-quantum line bundle, we can take an associated flat section. And for this for a smooth function f here, we also take its flat section, but yeah, sorry, I should have this sub m here, m the weight, the typo here. This OFM, we let it act on OS while the Bachmann-Fock action. And then what we can do is we can take the symbol, meaning that we simply take those constant terms. Now the output is in general only a smooth section of the pre-quantum line bundle, because we take the symbol here. Now this is a differential operator because at each point x0 in x, the flat sections OF and OS only depends on the infinite jet, or equivalent is the Taylor expansion of F and S at this point x0, respectively. So so this means this action is actually satisfies the locality condition, and obviously this is linear, and so we obtain a differential operator, gamma Fm. Yeah. Okay, so here we give a simple example, which is actually the first hint that we can generalize this Tolman lemma. So a simple computation shows that for weight m equals 1 case, the differential operator gamma f1, the weight m equals 1 case is exactly the one in Twyman's lemma. So that's the connection with this vector field xf plus 1 over k delta f. So that's exactly coincides with the differential in Twyman's. Okay. And in other words, the classical Twyman lemma can be written as the following orthogonality relation. You take two holomorphic sections of the pre-quantum line bundle, case tensor power, S1 and S2, you let gamma F1 acts on S1, and it's always orthogonal to S2 for any two holomorphic sections. So it's not surprising that for all weights m greater than or equal to 1, there should be a similar orthogonality relation. And this is indeed the case. And we can actually prove this. This is what we call the quantum Twyman lemma, because it sorry, I was offline for. Okay, so let me say this. So can you hear me?
Yes, yeah.
Okay. Sorry, I probably the internet connection problem. So the classical Twyman lemma can be written as this orthogonality relation, and this is gamma f1. So it's not surprising that for all weights m greater than or equal to 1, there should be a similar orthogonality relation. This is what we call the quantum Twyman lemma, and we prove this. This is our first main result. So we have the following vanishing for any holomorphic sections. So in other words, this for each m, we can obtain a differential operator sharing the same property as the one in the original Twyman's work. So gamma fm of S1 always lives in the orthogonal complement of this Hilbert space. Okay. So I'll briefly describe the proof of this theorem. So recall these differential operators is defined using the flat sections associated to both the function, I mean the quantum observable, and also the vector in the Hilbert spaces as follows. So using the fact that both OF and OS are flat under the Fedosov connections, we can actually show that the following top degree differential form on X. So this is how we compute this inner product. We have to take this top degree differential form, and then we integrate on X. And here, this bracket denotes the Hermitian inner product on this pre-quantum line bundle. So using this the flatness of OF and OS, we can actually show that this top degree form is actually an exact differential form. And then this boils down to a calculus problem. So we can simply apply Stokes' formula, which implies the vanishing result. And this is how we prove this generalized or quantum Twyman lemma. So I should. Okay. So let me mention some applications of this main result. So the first one is quantum symmetry. So this actually, for this quantum symmetry, we only need the traditional, the original Twyman lemma. But then actually, it actually pops up several questions. So how we can consider higher order of this generalization. But let me start with this one. So a quantum symmetry on a Kähler manifold is a vector field which preserves both the symplectic and complex structure of X. So why is this called a quantum symmetry? Because if it preserves the symplectic and complex structure, then it will preserve both the quantum algebra of observables and Hilbert spaces. So this type of vector field can be lifted to an action on smooth sections of the pre-quantum line bundle, and also its tensor powers, so L to the power k. So which also preserves the subspace of holomorphic sections, simply because this vector field preserves the complex structure. So this action is given by the following explicit formula. So that's the Lie derivative, which is the infinitesimal action here. So that's nabla v plus 1 over k mu of v. So mu of v here denotes the moment map associated to the vector field v. Yes. When I say moment map, it's the same as the Hamiltonian. So by using the original Twyman's lemma, we can show that the infinitesimal action LV, the infinitesimal action, can be actually identified with a Brising-Toeplitz operator. Okay, so why is this? So I will briefly describe this. So the Twyman's lemma here. So Twyman's lemma implies the following: we don't if we don't have this pi k here, we already have this equals 0. So it doesn't matter if we take a further composition with this pi k. That's the orthogonal projection to the subspace of holomorphic sections. And using this equality, you can see that the infinitesimal action here, because the infinitesimal action, so S here is a holomorphic section. So the output is still a holomorphic section. So it doesn't matter if we take a orthogonal projection, because that actually does nothing. And this Lie derivative here is of the following form. But then we can use the previous equality. So this nabla v acting on S can be written as minus 1 over k delta f times S. So this shows the Lie derivative acting on S can be written as follows. So, but on the right-hand side, both terms are simply multiplication by a function. The first one is minus 1 over k delta f. The second one is 1 over k f. And the right-hand side is exactly a Brising-Toeplitz operator. But if you think of this conversely, this is an interesting thing, because the right-hand side, because the right-hand side is actually a Toeplitz operator, but the left-hand side, it's an infinitesimal action, which is a first-order differential operator, meaning that for this kind of functions, their Toeplitz operator is actually a differential operator. But in general, this is obviously not true, because Brising-Toeplitz operators are only pseudo-differential operators. So it's interesting to ask the following question is like, so what are the analogs of these functions? So this function is very explicit, because it's the Hamiltonian of a infinitesimal infinitesimal quantum symmetry or a vector field. So what are the generalizations of these quantum symmetries? So this is what we call
40 minutes has passed. So could you please summarize?
Okay. Yeah, I'll finish very soon. So as another application, we will give an answer to the following question. So when is the Brising-Toeplitz operator associated to a smooth function, a holomorphic differential operator? And we have the following theorem. We can actually identify them. I mean, we can give an equivalent description. So for a smooth function, its associated Brising-Toeplitz operator is a holomorphic differential operator if and only if it's a quantizable function. So what does quantizable mean? Quantizable means that if you take the flat section, you have certain finite condition on this f, meaning that the flat section is only is contained in a finite rectangle in this diagram. Or in other words, its flat section has a finite weight instead of an infinite one. So that actually gives a equivalent description of holomorphic differential operators. Yeah, so I'm not going to say the proof here. Yeah, so I'm not going to say the proof. And some further question is that so for differential operators, we know that it can be identified with quantizable functions. So that's what we obtain from this via this quantum Twyman lemma. So are there like symplectic reductions of G invariant operators on M double quotient G, the symplectic quotient? What happens to their correlation function? Another interesting question is, so here we are basically doing quantum mechanics. So are there like higher analogs of this picture? For instance, in two-dimensional theories, what are the quantizable function and quantum symmetries in chiral differential operators? So this is also an interesting question. So the two-dimension, you can even ask a higher dimension, three-dimension or higher. Yeah. Okay. So yeah. Sorry. Pass a little bit. Several minutes.
Thank you
So
very much.
thank you.
Okay, so is there any questions or comments? From online participants, is there any questions? No. Okay, so time has passed, so let's thank the speaker again. Thank you very much.
Okay. Thank you.
Okay, so next talk is as scheduled.
Good.すごいもんやんな。なんでこうなってんの？うん。
Shanhan-san, it's okay?
Yeah, I think, yeah, it's okay. Can you see my
From
slide?
here, there is a participant list at the right up side. Could you move the participant? Yeah.
Okay, move it like this, or
Better. Yeah, okay.
okay,
Yeah,
okay.
perfect. Okay, so let's start. So are you ready?
Yes.
Yeah.
Yes.
Okay.
Okay.
Yeah. Okay, so the next speaker is Shanhan Chan-san from Nagoya. So he'll talk about twist field deformations in string field theory. So please start.
Okay. So thank you for the introduction, and I also want to thank the organizers of this workshop. I'm very pleased to be here to give this brief talk on string theory. So this work is based on the work of mine and my advisors and the co-authors during my master's at the University of Munich. It's entitled Twist Field Deformations in String Field Theory. So at the very first, I want to spend some slides on string field theory because most of even the string theorists may not be very familiar with this topic. Okay, so my uh, questions is that what is string field theory and what's it good for? So as we may know that the celebrated or notorious string theory computes some amplitudes, scattering amplitudes of particles. And these amplitudes are in fact obtained by summing up integrals on the moduli spaces of Riemann surfaces. And you can think of this summation as expansion of coupling constant. So by summing up integrals on Riemann surfaces with higher and higher genesis, we are actually summing up some Feynman diagrams, Feynman series. So we can see this theory is by definition perturbative because we are having a series to sum up, and also this theory is background dependent. This means that we have to choose a specific space-time background and then we can do a string theory around this space-time background. For example, we have to fix a metric like a Minkowski metric to do string theory. So a natural question is to ask is that if it is possible to construct an action from which the string theory amplitudes can be derived via Feynman diagram expansion. This is like construct quantum field theory from quantum mechanics, and this process is commonly known as the second quantization of string theory. And for the obvious reason, this is called string field theory. And yes, string field theory or SFT. And during the last few decades, the theory is developed more or less completely. Although it is rather complicated, we already have formulations for all the conventional string field theories. For example, n equals 0, this means that bosonic strings, and n equals 1 strings, which is conventional superstrings. And we have formulations also for both open and closed and heterotic strings. So this is the development of this string field theory. And another thing is that what is it used for? So what we have achieved in this theory is that we are firstly we are able to describe tachyon condensation in this theory. Tachyon condensation, which will be explained in details later, is actually a false vacuum in string theory, in perturbative string theory, and is best suited to be described in the second quantized framework. And secondly, we have some problems that in string theories are essentially field theoretic. So it's also better to solve these problems in SFT. For example, we have mass renormalization and instantonic contributions to the path integral. And there is a third application, which is still in a very primitive status, but is closely related to the first one, which is that we can carry out CFT perturbation theory beyond leading order in the framework of string field theory. So this is what we have achieved. But what is not done yet is that we still lack a fully non-perturbative formulation of string field theory. Although this is more or less this is somehow the first motivation for developing string field theory. By far, the action we have is still a perturbative BV action around a saddle point. So it's not fully non-perturbative. Recently, there have been attempts of majorly from Ashok Sen to generalize this by summing up all the contributions from instanton sector to get a non-perturbative action, but this will be not of major importance today. So okay, yeah. So let's take a closer look at the physics of tachyon condensation, because this is one of the major achievements in string field theory. So The theory, of course, has a dynamic variable, which here is a string field. Is a string field. This is nothing more but just a string state in the Hilbert space of string theory. For open strings, for open bosonic strings, the string field consists of the tachyon field Tk and the gauge field A and also the B field, which is standard string theory. And for in the string theory framework, the tachyon field is problematic because it has negative squared mass. So in conventional string theory textbook, we often say that bosonic string is problematic. But from a field theory perspective, this can be modified because if we have a negative squared mass in field theory, we know that we are just doing a perturbation on a round vacuum. For example, if we see this figure, we can see that the vacuum that t equals 0 is not a real vacuum, it's the maxima. So a physical vacuum would be that the tachyon field falls into some real vacuum, which is a minimum, and this minimum is called the tachyon vacuum. So Ashok Sen conjectured that the open string vacuum, which is the convention one that the spacetime is filled by a D25 brane, should decay into the real vacuum, which is the venicity of D branes. This means that we have no D branes for the open strings to be attached to, and there is no open strings accordingly. This is called the tachyon vacuum. And this conjecture is proven by constructing an analytic expression for this tachyon vacuum in SFT equations of motion. And it was done by Schnabel in 2005. So apart from the tachyon vacuum, there's another kind of force vacuum, which is the marginal deformation of what is string conformal field theory. First, we mentioned before that the string field theory should be background independent. So it's independent of the space-time background that the string theory is defined on. This means that if we have a collection of different string backgrounds, maybe the metric or D-branes configurations and so on, and these different backgrounds should correspond to different classical solutions to string field theory. In field theory, you can imagine vacuums are just classical solutions to the equation of motions, right? So this is similar. And it also corresponds to different worldsheet CFT. This is obvious. And so deformation of the worldsheet CFT can be represented. This is the CFT content. It can be represented by an operator of conformal dimension 1, and this is called a marginal operator. But the story doesn't end here because not every marginal operator represent a valid deformation, and those that do represent a marginal deformation are called exactly marginal. So identifying exactly marginal deformations in conformal field theory is an important subject. So maybe we can find some insight from string field theory because every exactly marginal operators are valid string backgrounds. We have to deform it into another valid string background. So therefore they have to be solution to the classical string field theory equation for motion. And before we dive into real life problems, we have to review some contents of the string field theory action. So now we have both actions for open and closed strings. And basically you can see here now is polynomial action of psi. Psi is the string field, is just a vector in the Hilbert space of strings. And Q here is a linear operator called the BRST operator. And this is the connecting term. And we have cubic terms, quartic terms, and so on and so forth. And for open strings, the degree of the string field is defined by the shifted Grassmannian. And we have a product, nth product that satisfy the A infinity relations. For closed strings, the degree is just the Grassmannian. So if it's bosonic, it's degree 0, and if it's fermionic, it's degree 1. And the string field should be restricted to some subspace of the Hilbert space. This is technical, so won't be explained further here. And the nth product satisfies the L infinity relation. Yeah, so we have a specific setup here that is the string theory setup for ADHM instantone. This let us think of k d-1 branes sitting on a stack of n d3 branes. So this basically is the string theory setup for ADHM instantone, and you can think of this d-1 brane, which is just a point in the spacetime, as the instantones of the Yang-Mills super Yang-Mills series in the n3 branes, which is the 4-dimensional spacetime. Yeah, and the n is the number of it means that it has a SUN gauge group, and k represent the winding number. But this setup is not exactly true because D-brane bound state system. Now we have a D-brane bound state system of infinitesimal size. So it's just an approximated string background. This just like the point like instantone is an approximated solution to the Yang-Mills equation. So one would like to deform this background into some finite size one. Then it's an exact solution. To deform this, recall what I mentioned before. We should first identify the marginal operators. Here, the operator relevant is the twist field, which this is a product of the twist fields along for the first 4 spacetime dimensions. And the twist fields has the fact that change the boundary condition of strings. So if we have a string stretching between 2 different types of D branes, for example, here is D-1 brane and the D3 brane, the boundary condition of this of 2 endpoints would be different. So the twist fields has the effect if you insert it into 0 or infinity, it will change the boundary condition on the worksheet. So we have this capital delta is the twist field, but it's not a marginal operator. But we can make this into a marginal operator by inserting some ghost fields in. It's just like a standard string theory trick. So this is a marginal operator because it satisfies the equation, the linearized equation of motion QV equals 0. But it doesn't satisfy, but it is not exactly marginal because it doesn't satisfy the full string theory equation of motion, which looks like this. So we have quadratic and cubic and higher term. So this equation, this full equation of motion is satisfied only if we deform. We can do perturbation theory. If we deform this using a parameter rho, we will see that in the following that the rho is just the size of the d-brane instanton. And if we deform this and at each order, we will have an equation that they have to satisfy. So we can solve this order by order, and at each order it's just a linear equation. So it's, but we have to take care of this because the BRST charge is in general not invertible because it's a homological cohomological co-boundary operator. So we also have a solvable condition at each order. Here, P0 is a projector onto the subspace that Q is not invertible. So we project the inhomogeneous part onto onto this subspace, and it should be 0. Otherwise, we cannot solve the equation of motions. So for SU2 group, which is the most simple non-abelian case, we can compute the correction to the gauge field. And this result, which is to the second order of rho, is exactly true. It exactly agrees with the ADHM construction of the instanton if we expand for small rho. And what's more intriguing may be that is the solvable condition that here from string field theory, if we put it into the solvable conditions, we get some constraints on the moduli of the deformations. And this constraint is the well-known ADHM constraint. So basically, we see that there is an equivalence between the string field theory approach and the field theory approach. Okay, so this machinery can also be moved to closed strings. Here, the physical meaning of twist fields in closed strings is that, for example, if we see the illustration here, that if n closed strings ends in two different places, but they only differ by a minus sign, then by identifying x with minus x, we get an orbifold, and Z2 orbifold on the space-time. So this twist fields represent an orbifold construction of the space-time. So there, if we do this deformation constructed from the twist fields of closed strings, unlike the previous open case, we'll find out that there is no constraint on the moduli, because now we have two separated holomorphic and anti-holomorphic part in closed strings. And because there's no constraint at up to the third order, we can take the moduli any as we want. So if we choose this specific moduli that they equals, we can easily compute the correction to the metric, just like what we did before to the gauge field. We see that the result is
20 minutes has passed, so
yes.
could you
I'll
please,
wrap it up.
summarize?
Okay, yeah. So the last conclusion here is that if we compute the Kähler form and we compute the exterior derivative of this, we will see that it gives a non-vanishing result. So this is no longer a Kähler form, and we see that the spacetime is no longer Kähler. And since it's still an ongoing work, we still have some questions. That is, what's the relation of this to the resolved space? Because the standard folklore of string theory is that the string somehow fills instead of the orbifold, it fills the resolved resolved space in the space-time. And another question is that will there be higher order constraint on the moduli? Because unlike the open case, it basically ends at the third order because we already have the result of ADM HM constraint. But now for the closed strings we do not have the counterpart of that. So it's still worth exploring. And that's basically my talk. And thank you for your patience.
Okay, thank you very much. So is there any question or comment?
Oh, excuse me.
Yes,
So
please.
I'm sorry that my question is slightly outside of your main topic. And
Okay.
beginning, you mentioned tachyon condensation.
Yes.
And from the first talk in this morning, we learned that the condensation is often related to topological defect, right?
Yes.
So
Yes.
can you see some kind of topological defect in tachyon vacuum?
I don't think so. As far as I know, because here the tachyon condensation is just sometimes you may say that, for example, the orbifold construction, because for example, for an orbifold construction, we have a singular point, right? And then because of the tachyon condensation, it will decay into some resolved spaces. And the singularity was resolved in this sense. So it may be related to topological defect in this sense, but
that doesn't seem to be related to the topological defect. But I suppose in the tachyon condensations, D-branes play an important role, right?
yes, I do think
So I suppose such kind of D-brane looks like some kind of defect. No.
yeah, yes, you can say that, but sometimes in the absence of D-branes, there is also some so it's just from a field theoretic point of view, it's just moving around the different vacuums. But yes, I agree that in the most cases, the D-branes or topological defects play an important role. Yes.
Okay, thank you very much.
Yeah, thank you. You're welcome.
So any other questions or comments? If not, so let's thank the speaker again. Thank you very much. Okay, so afternoon session will start as scheduled at 1:30 in China and at 2:30 in Japan.